Slowly, but it goes, all right? It keeps going up forever. It's just not very fast. It's not like exponential where it just takes off. Here, the log function grows slowly as you go out to the right. So, as you go to infinity, the graph goes to infinity as well. They both go up together, yes? Now, to the left, we have an issue. Log functions have domain restrictions, which means you can never plug a negative number into a log, and you can never plug 0 into a log. How do you know? Because you took college algebra, you were told that was the domain of a log. So you're never allowed to have 0 or negatives in here, which means our graph should never appear. There should be no graph to the left of the y-axis, ever. But what does happen is that as we get closer to 0, as we try and get closer to 0 on the x-axis, what does our function do? It dives down. It never crosses the y-axis, right? It asymptotically heads to negative infinity, which is that second limit. As x approaches 0 from the right, the function heads to negative infinity. Do you all see it on the graph? Everyone see it? So on a log function, to the right it goes to infinity. To the left, you can only approach 0, and it dives down to negative infinity. This is only if a is bigger than 1. If a is less than 1, here's what it looks like. It's a little bit different. So the blue is if a is less than 1. If a is less than 1, then what happens as we go out to the right? It heads to negative infinity this time, right? It's going down and down and down and down and down. And as we head to 0 from the left, right, as we come this way, it takes off to positive infinity instead of going down to negative infinity. Good thing we don't have an odd number of fingers, right? That would be a weird situation, wouldn't it? If we had like 13 fingers, then we'd be in base 13. But I think it would just be weird. Probably not. We'd be used to it, right? All right. Properties. What are properties of logarithms? You might remember these properties from college algebra. It was this section in college algebra where you were asked to expand or condense logarithmic expressions. We had to take an expression like pull it apart or push it all back together. It's these properties right here. So let's look at these. Let's make sure we understand them. The first property of logs says that if you have multiplication of two things inside of a single log, right? See, there's one log and there's multiplication inside. You are allowed to split this into two logs, right? Two separate logs where you put the x in the first one, the y in the second one, and now you put addition between them. That is a property of logs. So it's kind of like, we were talking about the properties of exponents a second ago. We said if you have a to the x times a to the y, then all you do is you add the exponents. Like that's a property of exponents. But what's a property of logs? This is a property of logs, and it's different than that. And then this one says if you have a single log with division inside, it turns into two logs with subtraction. Do these look familiar? I mean, I know you covered it at some point, but it's just been a while. I will tell you, in calculus, these things pop up all over the place. Like you'll just be doing a problem, and all of a sudden it's like, oh, just use that property of logs. You're like, oh, okay, I didn't know I could do that here. Yes, if you ever have this, you can use this. And it works both ways. You can go from here to here, or if you have this, you can go from here to here. So it works left to right and right to left. The third property is one of the most important properties that we will use for logs right there. This property says that if you have a single log and you have something to a power, you are allowed to take that power and bring it out in front of the log as a number being multiplied. Let me give you an example, a specific example of this. If I wrote log base, let's say 3 of x to the 5th power, that would be, according to that property, 5 log base 3 of x. That's just that property being used. That power can come out in front. Okay. Back when we were talking about exponentials, I said there's one very special one, right? When it comes to logarithms, what's the very special one? The natural log. It's the one that is the inverse of e to the x. So back when we were talking about exponential functions, I said this is the important one, e to the x, right? And now there's a special log function, which is this log function right here. It's log base e. Remember that base on the bottom, a, can be any positive number. It just can't be 1. So if I make that base e, then this is a very special function that we call the natural log. And instead of writing that, we write that. This is a place in math where I wish we never did this. I wish that this was never, like we had never ever come up with that notation. I wish. I mean, I can't undo it now. But it confuses students because I think when students see the natural log, they lose sight of the fact that it's just the log function of base e. Now, historically, there's a reason why we went to this notation. It actually has to do with typewriters. Back in the day when people would type things, and if you ever had to subscript, it was a real pain in the ass because you'd have to stop typing and then like turn the little drum and then type the letter E and then turn the drum back and then continue typing. And so these scientists and stuff, or people who were doing STEM, would be writing these papers, and they would have to write the log base E like hundreds of times in the paper, and it was a real pain. So they just said, hey, forget it, just do that instead. You never have to stop typing. It's easier. Does that make sense? And so it's stuck, and we still have it, unfortunately. Okay, so we have the natural log is the inverse of the e to the x. Let's look at some properties. The whole idea of the inverse, the logarithm, is to undo the exponential. So look at that first property. It says that if you take the natural log, and inside of it you put the e to the x, these two functions are inverses of each other, right? So they kill each other off. So it's like you first try and plug x into this, and then you do its inverse. The x should come out unchanged. Look at it like a chain of events. X goes in to the e to the x function, comes out, and then that goes into the natural log function, comes out as natural log of e to the x. But see, this function undoes that function. So it's kind of like car wash. The car goes in, gets clean, and then there's another machine that puts all the dirt right back on the car, and it comes back exactly the way it started. Right? That's basically what's happening here. The second property is the reverse of that. First, the x goes into the dirty car wash, and then it goes into the clean one. At the end of the day, it comes out unchanged again. We all know that e to the 0 is 1. Do we all know that natural log of 1 is 0? That you should know. This is 1 because any number to the 0 is 1, right? Any number to the 0 is 1. The reason why this is 0 is that same sort of picture. If you were to take the number 0, plug it into the e to the x function, it comes out as 1, right? If 0 goes into this, you come out as 1. The natural log function should reverse that, shouldn't it? The natural log should take that 1 and send it back to 0, because that's what inverses do. And then you should also know that the natural log of e is 1. That property right there is actually, property 5 is actually just property 1, but replace x with 1. Right? If I replace that x with 1, then that's just e, isn't it? And then that would be like e to the 1. And so you get natural log of e to the 1 is 1. So 5 is just number 1 at a specific value of 1. There's one more thing, and then we're going to start doing calculus. There is this formula called the change of base formula. And a lot of you, on your calculators, you usually only have 1 or 2 keys on your calculator. On your calculator, you usually only have the natural log key. Some calculators will also have the log key. This key is, of course, the natural log. That's log base E. Do you all know what the base is on this one? 10. This is base 10. Your calculator only gives you, at most, 2 keys for logs. Log base E, log base 10. The reason why you don't need more keys for all the other bases is this property right here. This property says that any logarithm of any base can be converted to this using just that 1 key on your calculator. So like if you wanted to do log base 4 of 8, if you wanted to figure out what that is, all you'd have to do on your calculator is natural log of 8 over natural log of 4, and that would be your answer. This in no way was designed to be a thorough review of exponential and log functions. I do have an expectation here that you have some understanding of these. We'll see how it plays out, how comfortable you are with it as we go through this. But really, our goal is to take derivatives of these functions. We want to know what their derivatives are. So let's get into that. So 3.3 is the section you have homework out of. All right, this is the section that you need to do homework from. Derivatives of exponential and log functions. So it's kind of weird here, but we're actually going to start with the log function. We're not going to start with the exponential. And I think what I'm going to do here is, instead of that, I'm going to do it here. So the note is this. If you take log of any base of x, and you take that function and take its derivative, what it is 1 over x times the natural log of a. I'm not going to prove that because y'all voted a long time ago that I only proved a few derivatives for you, so I'm just giving this to you, all right? That's the formula, all right? Let's do an example. If f of x is log base 3 of x, find f prime of x. All right, so we just use that formula, right? The derivative will be what? One over x, natural log of 3. Thank you. Right? That's just plugging into the formula. That's it. There's no magic here. Okay? Now, I'm going to tweak the problem a little bit. Let's do something a little different. What if we have this? F of x equals log base 3. This time, I'm going to put inside x squared plus x. Now you don't have inside, right, the argument. Here the argument of this log function was x. So I just did exactly what this formula says. Here, the argument inside is not just x, it's x squared plus 1. So that's kind of like, think of it like if this said sine of this, right? It's composition. You have a function inside of a bigger function. So we're going to need chain rule. Right? We're going to have to apply the chain rule here. What's the inner function? What's the inside? x squared plus x. The outside is the log base 3. Okay? So we start with the log base 3. What is the derivative? What is the derivative of log base 3 of my hand? Follow that formula. 1 over what? What's the derivative of log base 3 of my hand? 1 over my hand, log 3, natural log of 3. Right? So it'll be 1 over, in parentheses, x squared plus x, then natural log 3. See, it's the same chain rule we've been doing, but now we have a new derivative formula that we have to be able to use with it. Am I done, though? No, I need to multiply this by what? Because chain rule says then multiply by the derivative of the hand in there. So what's the derivative of this? 2x plus 1. Yeah? Do I need that in parentheses? Yes. There you go. That's the derivative. Let's do another one. What about f of x equals log base 3 of sine x? Do y'all see the composition again? Take 30 seconds, or not 30 seconds, take 20 seconds, see if you can come up with that derivative. Just the raw derivative. And I'll ask for a volunteer. Leslie. It's very similar to the previous one, right? Very similar? All right, let's hear from somebody. You want it? Go ahead. 1 over sine x, sorry? Times ln 3, natural log of 3, times cosine x. Now I heard you say parentheses. You may have put parentheses here, and you could have put here, but those are actually not necessary because this is only a single term. So we don't have, here we have 2 terms, right? So we have to worry about distribution. Here we only have 1 term, so I don't need it, but it's not wrong to have it, all right? That, good? Now, of course, you could slide the cosine on top, couldn't you? Yeah? And then cosine divided by sine is actually cotangent, but we're not, let's just move on, all right? I have another one for you. How about this? I want the derivative of this. What do you see? Product? Everyone see product rule? Your product is right. It's my squeaky blue one. There we go. There's your product, right? So you're going to have to do product rule on this, right? Derivative of the first one times the second, plus derivative of the second one times the first one. Here we go. Who wants this? Yeah? Huh? Go ahead.
3x.
3x. Hold on. 3x.
Oh, 3x squared.
Squared. Okay, there you go. Times
Log 3.
log base 3 of x. Okay. Plus
1 over x times natural log 3 times x to the cube.
Yep, that's it. There you go. That's your raw derivative. That's the derivative of the first one times the second one, plus the derivative of this we did, that was the first problem we did, right, is that times that. Again, you could clean this up a little bit because, you know, you could cancel one of these x's, right, and make that a 2. Move that on top. And we're starting to get close to that point in time where we're going to have to start doing something with these derivatives. So I've kind of conveniently avoided the algebra, but we're going to need algebra pretty soon. All right, you get the idea? Everyone got the idea? Okay. How about this one? How about natural log of x? What's the derivative, right? That's the question. By the way, let's put a big star next to this one because this is a really important one. All right, so what is the base of this log? What is the base? If it's really a log, right? Like this is log base 3. What's the base of that log? Log base e, right? That's log base e. For real, that's what it is, right? So I'm actually going to write it that way so that I can do the formula, right? So I can use this formula. So if that's really log base e, then the derivative should be, let's see, I'm going to go 1 over x times natural log of what? Natural log of e, right? Natural log of e. But what is natural log of e? Where are my notes? Hold up. Not. Go to my properties. Where were they? Here we go. Right? Here are properties of logs. Which was it? Fifth property right there. What's natural log of e? 1. Right? The natural log of e is 1. And that means that this is just a 1, isn't it? And that means my answer is just 1 over x. Right? So the big takeaway of this is this. The derivative of the natural log of x is 1 over x. It's the only one that doesn't have that little natural log, like this one had a natural log 3 here, right? We always had to have that natural log 3. Whenever you have natural log as your function, this will always turn into a 1, which means you don't have to worry about it. It's always going to be just 1 over x. So let's see if you can adapt this. Try this example. Let's say you have f of x equals natural log of, let's go x squared plus x again, something like that. Composition, right? Composition. Starting with the outer function first. The derivative of natural log of my hand is what? Just 1 over my hand. You don't even have to worry about the natural log e thing, right? That's what I'm saying. You just go straight to the derivative of this is 1 over it, 1 over that, what's inside. But I'm not done, right? Times what? Times the derivative of what was in here, which is 2x plus 1. And then you could take that whole thing and just slide it up top if you want. A lot of textbooks will do that. They'll just move that up there. In fact, a lot of textbooks will do this. They'll say, hey, look, if you're ever trying to take the derivative of the natural log of something, here's what you do. Whatever's there, you put it on the bottom. And then you take the derivative of it and put it on top. That makes sense? Like, this right here, this denominator is just what was in here, and the numerator is just the derivative of what was in there. That will always happen when you're talking about a natural log. You could say it this way. That's the derivative of the inside of the log over the inside of the log, right? The derivative of the inside over the inside itself. How about this? Natural log of let's go cosine x. Composition again. Now the way I do it, I've always done it this way, is I just follow the formula. I'm going to go 1 over whatever was here times the derivative of what's in there. Right, because the derivative of cosine is negative sine. Follow? Now if I clean that up, I get negative sine x over cosine x. And I know that that's tangent, so I'm just going to put negative tangent x. I cleaned that one up because it was easy to clean up. Yes?
On the test, are you going to want us to like try to clean up as much as possible, or are you going to be okay with just like
On this next test, there will be some problems where you will have to do a little more work on it. It won't be, like, there will be a section where it's just, where I want the raw derivative, but there will be also other problems later where we're going to have to do something with that derivative. So you're going to have to do some algebra.
Will you specify the extractions?
I'll specify it, yeah. I'll just say find the raw derivative or something like that. Let's do one more of these. Or how about 2 more? I'll do 2 more. How about I put them up here and you see if you can get them. Take a few minutes. So first one here, let's do x, x ln x. That's a pretty neat one. And then this one, see if you can find the derivatives of those. I'll give you a few minutes. Raise your hand real quick when you get the first one. You got the first one? Okay. Yeah. Stand up and do 10 jumping jacks when you get the second one. No, I'm kidding. What are y'all using to do the first one? Because I know some people might be struggling. Product rule, right? You should be using product rule on that first one. Good. Do you do product rule on the second one? Within a chain rule. Yeah, so you have to do chain rule, but then there's a product rule in there as well. So, okay, keep going. Anyone have a question? I can come by and clarify. I've put the raw derivatives up there. How many of you got those? Okay, good. Anyone have a question over any part of it? You sure? Okay, if there's no question, then we are going to move on. Your homework, we're still in the same section, okay? We're not done, but your homework will give you problems where you have different variations of chain rule, product rule, quotient rule. Basically everything you've learned in the past now mixed in logarithmic functions and exponential functions. We haven't talked about exponential derivatives yet. So this is the derivative of a log. What's the derivative of an exponential function? All right. So what if you take a to the x and you take its derivative, right? What do you get? Well, here's what you get. You get exactly the same thing you just had, a to the x, but then you have to multiply that by a number, and that number is the natural log of a. I should point out that all of these formulas are on your formula sheets, okay? If you go to your page on derivatives, it's up there at the top near the product rule and quotient rule and chain rule. It's all up there, or it's up there somewhere. It's there though. All right, let's see this in action. All right, let's see this in action. I'm going to do this a little bit different notation for this. I'm going to say this. What if I ask you to find the derivative of 4 to the x? What's the derivative of 4 to the x? According to the formula, it's what? 4 to the x times the natural log of 4. I didn't mention this earlier, but I hope everyone realizes that the natural log of 4 is just a number, right? If you got on your calculator, did natural log of 4, this would just be a number. So this is a number times a function. So it's like we're scaling the function. So 4 to the x, if you want to know its derivative, it's itself, but you have to scale it, right? You have to kind of like stretch it out or shrink it, depending on what this is. Let's do another one. What's the derivative of 7 to the x? Well, itself, right? Times natural log 7, right? No magic, no hidden thing here. I mean, it is as straightforward as it looks. What about pi to the x? Well, pi is just a number, right? Just like 7, just like 4. So the answer here should be pi to the x times natural log of pi. And again, you could do natural log of pi on your calculator. Got it? Here's the interesting one. E to the x. This is the special one. Because according to the formula, this is what?